Need a professional website? I created one for our
Hello students, I am Deepak Khurana and you are welcome to Ekeeda. This is the biggest platform for video lectures for engineering graduates and undergraduates. So today I am going to discuss some of the topics of strength of materials. So the topics are basically thermal stresses, elastic constants and Poisson's ratio. I will discuss these topics today. And I will summarize the topic first, the formulas related to the topics, and then we will solve some gate questions for these topics. So let us start the topic. Let us brief first. What are elastic constants? How many elastic constants are there which are used in strength of materials? So basically we have 4 elastic constants. What are these elastic constants? I'm not going to give the full theory, but just I am summarizing the topics. So mainly elastic constants are E. This is Young's modulus of elasticity. Young's modulus of elasticity. Then we have, and how to find out E and what is the unit? That is Newton per meter square, right? 1 Newton per meter square is 1 megapascal. You know, 1 Newton per meter square is 1 Pascal. And 1 Newton per millimeter square is, that is 1 megapascal, right? When you convert it into Pascal, it will be 1 megapascal. You have to remember this, right? 1 megapascal. This is 1, right? So this is 1 megapascal. So E is the Young's modulus of elasticity. Then we have G, modulus of rigidity. That is called modulus of rigidity. Unit is same unit, Newton per meter square, or 1 Newton per millimeter square, or 1 megapascal, right? And then we have bulk modulus. Bulk modulus. Again, unit is same because these are similar things. Bulk modulus. And then we have the last constant, that is Poisson's ratio. Poisson's ratio, right? And this is unitless. This is unitless. So in theory lecture you can read these things, and then you will be able to do the questions on this. I hope that you have read some basics of strength of material, right? Now E, G, K and mu are the constants. And how to find out E? What is E actually? This is the normal stress upon normal strain. Normal stress upon normal strain, right? This is how we find the E. And how, from where it came? It came from Young's modulus. That is the normal stress upon normal strain, right? So this comes from Hooke's law, basically Hooke's law. So stress upon strain. This is the modulus of elasticity. E stress upon strain. So you have to remember this formula. Whenever required, we will use this. Normal stress upon normal strain. This is the Young's modulus of elasticity. Came from Hooke's law, basically, right? So it came from basically Hooke's law. Then we have a modulus of rigidity. That is shear stress upon shear strain. Shear stress upon shear strain. Shear strain. So this is shear stress upon shear strain. So you have to remember this also, that is tau upon phi. I'm writing here tau upon phi. So this is the modulus of rigidity, right? Then we have third, bulk modulus. Bulk modulus. Bulk modulus is basically, bulk modulus come into picture when there is a three-dimension body, right? Three-dimension body is there. Suppose we have a three-dimension body. I am making the body here. Suppose this is a three-dimension body, and you have applied the stresses in three directions, and the stresses are equal, right? You have applied the stresses, suppose sigma, in all three directions, and in all three directions the stresses are equal. X direction, Y direction, as well as Z direction is there, and the stresses are equal in all directions, right? Sigma is same. So what do you do in that case? We define, and there is change in volume due to these stresses, so we define the bulk modulus for this case, that is a direct stress, or one of the stress, direct stress per unit volumetric strain, right? Volumetric strain, right? Basically this tells about the compression or expansion of a body when stresses are applied, right? So K is basically sigma by volumetric strain epsilon V, right? So K is sigma by epsilon V. You have to remember this also. So these are the three constants, E, G, and K. E is the normal stress upon normal strain, and G is the shear stress upon shear strain, and K is the direct stress upon volumetric strain, right? So these three types of stresses are there, right? Constants are there. One more constant is there, that is the Poisson's ratio, right? So let us define the Poisson's ratio also. Poisson's ratio. So let us talk about the Poisson's ratio. Poisson's ratio. Poisson's ratio. What is that Poisson's ratio? It is generally symbolized by mu. Mu is the symbol for that Poisson's ratio. This mu, Poisson's ratio, is the ratio of lateral strain upon linear strain or longitudinal strain, upon linear strain or longitudinal strain, right? So what is that? Suppose we have a bar. Suppose we have a bar like this. And if we are applying a force or stress or load in this direction, suppose we are applying a force in this direction, suppose linear direction, I have shown by arrow, right? So suppose a load is applied and there will be stress developed in this direction. So there will be increase in length of this bar, this specimen. There is some increase in length of this bar, as well as along with the increase in length, there is decrease in dia. There is increase in length. I am showing with dotted line. There is some increase in length, as well as there is also decrease in dia. Diameter is decreased, right? So what will happen? That length is increasing and dia is decreasing. Length is increasing means that linear strain, I am showing this linear strain by epsilon, and longitudinal lateral strain by epsilon dash, suppose, right? So linear strain, it means that the linear strain will increase, and the lateral strain will decrease, right? So this is the relation. The strain in x direction is increasing. Suppose this is our x direction and this is our y direction. So in strain in x direction is increasing, that is linear strain, and strain in y direction, and we have applied stress only in one direction, but there is the effect of that in other direction also. So Poisson says that the ratio of these two strains, lateral strain and linear strain, is always constant. That is given by Poisson's ratio, right? So Poisson's ratio is basically the ratio of the lateral strain upon linear strain. So this is the Poisson's ratio, right? So now you understand the different elastic constants, that is modulus of elasticity, modulus of rigidity, bulk modulus, Poisson's ratio, right? These are the four elastic constants, right? There is some relation between these constants. What is that relation? That we are going to discuss. You can take the screenshot of this if you want to take. So there is a relation. What is relation between E, G and K? You should remember that, right? Relation, and the formula in GATE exam are directly used for these relations. Relation between E, G and K, and mu also, right? Mu also, E, G, K and mu. What is the relation between these constants? What is the relation between these constants, right? So the relation between E, G, K and mu are that you should remember these formulas, right? So E is equal to, one of the relation is E is equal to 3K 1 minus 2 mu, right? This is the very important relation between E and K, E, K and mu. This is the relation between E, K and mu. You should remember this. E is equal to 3K 1 minus 2 mu. Similarly, we have relation between E and G, that is E is equal to 2G 1 plus mu, modulus of elasticity and modulus of rigidity. So this is the relation E, G and mu. So relation is between E, G and mu, right? So this is the relation. And there is one more relation also. There is one more relation also, that between, when if we can replace mu, and between E, K and G. So that relation is E will be equal to 9 kg. It is not kilogram, it is the constant K and G, divided by G plus 3K. G plus 3K. This is the third relation between E, G and K, where the mu is not required, right? So you can remember this one equation, second equation and third equation. You should remember this, right? So this is the relation between E, G and K. So three relations are there. You should remember E is equal to 3K 1 minus 2 mu, E is equal to 2G 1 plus mu, and E is equal to 9 kg by G plus 3K. These three relations are there. You should remember this, right? Now, apart from this, you should remember the volumetric strain, because bulk modulus is related to volumetric strain. As we already discussed that K is equal to sigma by epsilon V, volumetric strain, right? So what is volumetric strain? What is basically volumetric strain, right? So K come into picture when there is three-dimension picture is there, body is there, and the stresses are applied, right? So suppose this is the three-dimensional body, and there is some stress in y direction, suppose sigma y. Sigma y is there. In x direction, suppose sigma x is there. And in z direction, suppose sigma z is there. Okay. So how to find out volumetric strain? I am writing directly formula, although in theory lecture this is totally derived, right? So we have derived this formula. So that is equal to sigma x plus sigma y plus sigma z by E 1 minus 2 mu, right? So you have to remember this also. Wherever required, we will use this equation also. So this is the fourth equation. So these four relations are very important for elastic constants, right? So you should remember these four relations: relation between E, K and mu, relation between E, G and mu, relation between E, G and K, and then the volumetric strain in terms of sigma, mu and E, right? You should remember these relations. Is it okay? Now, if this is clear, it is summarized, right? In theory lecture, these all things are derived. Here we are using directly formula where required, right? So if this is clear, now we can solve some questions of GATE exam based on these relations, elastic constants, right? So what are the constants? What are the relation? So let us solve some questions here, right? one of the question is there that a 200 by 100 by 50 steel block is there. Steel block is there, 3-dimension block is there. So this is a 3-dimension block, suppose. This is the 3-dimension block. So 3-dimension block is there, 200 by 100 by 50. It means volume is given. All the 3 dimensions are given, that 200 by 100 by 50 millimeter cube. This is the volume, right? Volume is given of this steel block. A hydrostatic pressure of 15 megapascal is applied. Hydrostatic pressure is basically in the by Pascal's law, the hydrostatic pressure is equal in all directions. If we put a body in water, so due to Pascal's law, the pressure will be same in all directions, right? Here pressure means stress. In terms of strength of material, we can say that this is a stress, right? Compressive stress basically. Here pressure, hydrostatic pressure, we mean hydrostatic pressure meant that this is compressive stress. Compressive stress. Right? And it is given that this the value of this hydrostatic pressure is 15 megapascal. So this pressure is same in all directions, right? It is compressing with the same intensity P in all directions, right? Because Pascal's law say that the pressure is same at a point in the fluid, is same in all directions, right? So this is the hydrostatic pressure in all directions, isn't it? Now, if this pressure is same and this is 15 megapascal, the Young's modulus of elasticity is given 200 gigapascal. E is given to us, that is 200 gigapascal. This is given, and also the Poisson's ratio is given mu, that is 0.3. Poisson's ratio is given. We have to find out the change in volume. Change in volume. This we have to find out, right? This is unknown. How to find out the change in volume, right? Now, as we discussed earlier in the last slide, that the volumetric strain is given by sigma x plus sigma y plus sigma z by E 1 minus 2, right? Remember this formula. This formula is very important, right? Just we have discussed this formula. We are not deriving this formula, just writing this formula. Derivation is given in theory lectures. So volumetric strain is sigma x plus sigma y plus sigma z by E 1 minus 2 mu. So volumetric strain can be given as, now from here, now sigma x, sigma y, sigma z is P here, pressure, hydrostatic pressure, and it is same in all directions. So sigma x, sigma y, sigma z is basically P. So we can write that sigma x, sigma y, sigma z is basically compressive stress, which is equal to hydrostatic pressure, which is given by 15 megapascal, right? It is P. So volumetric strain can be written as 3P, because sigma x, sigma y, sigma z are added up, right? 3P by E 1 minus 2. तो ये हो जाएगा 3P by E 1 minus 2, right? Now, if it is so, then we have to find out change in volume. And what is volumetric strain? What is volumetric strain? That is change in volume per unit volume. This is the definition of volumetric strain, right? Every type of strain. Change in length, suppose longitudinal strain, that is change in length upon original length, right? Lateral strain, change in dia upon original dia. So in this case, this is volumetric strain, change in volume upon original volume. So from here, we can write that volumetric strain is change in volume per unit volume, that is 3P by E 1 minus 2 mu. So from here, we can write change in volume as 3PV by E 1 minus 2 mu, right? So we can further solve it. Now, everything is given to us. We can directly apply the formula and find out the value. So, apply the formula. Delta V will be equal to 3P. What is P? P is given to us. That is 15 megapascal. Keep it in megapascal. 15. Volume. Volume is given to us. That is 200 by 100 by 50. This is the volume. Volume is given to us, right? And keep it in millimeter so that the answer may come in millimeter cube. Divided by E is given in gigapascal. Convert this into megapascal. So this is 200 gigapascal. When you multiply it with 1000, it will become megapascal. 1 minus 2 mu is given to us, that is 0.3. When you solve it, you will get the final answer as delta V will be come out to be. So final answer is, solve it, use calculator and get the final answer. So it will come out to be 90 millimeter cube, right? So it will come out to be 90 millimeter, right? So change in volume is delta V is 90 millimeter cube. So this is the answer of this question, right? So basically the option number B is correct, right? Option number B is correct, right? So this is how we solved the questions of elastic constant. This was the GATE question of 2003. This was asked in 2003, right? So this was the question of GATE 2003. So you can take the screenshot of this question and then we can proceed for next question. Let us discuss the next question, that is Poisson's ratio. The question is that the Poisson's ratio for a perfectly incompressible linear, the Poisson's ratio of a perfectly incompressible linear elastic material is, we have to find out the what is the Poisson's ratio of a perfectly incompressible material, right? We have given 4 options and we have to find out what is the value of Poisson's ratio for incompressible material, right? This question was asked in GATE 2017. So this is a good question, and there is a fixed value of elastic incompressible material, and that is 0.5. The answer is 0.5, but how we get the answer, this we have to discuss, right? This is the answer that for a, and you should remember it, right? Directly you should remember it, that the Poisson's ratio of a incompressible material is always 0.5, and in fact the Poisson's ratio cannot be greater than 0.5. It is always less than equal to 0.5, right? It cannot be higher than 0.5. So how we get this value 0.5? The elastic constant ratio is Poisson's ratio is 0.5. How we get that, right? So suppose we have a incompressible material. It means that the material has constant density, right? So density of the material is constant. Density of the material is constant. It means that you are applying forces and density of the material is not changing. And if the density of the material is not changing, it also means that there is no change in volume of the material, because if density is constant, it means volume is constant. So there is no change in volume of the material. So delta V is 0. This is very important. This is very important. For incompressible material, the change in volume is 0. Right? So you should remember this thing, right? Now we can proceed. We know that volumetric strain is given by that is sigma x plus sigma y plus sigma z by 2, or you can write we can write formula direct, that E is equal to, we know formula, E is equal to 3k 1 minus 2 mu. We know this formula, we can use this formula. E is equal to 3k 1 minus 2 mu, and k is, we have defined k as sigma by epsilon v, stress, direct stress upon volumetric strain, right? And what is volumetric strain? What is volumetric strain? Volumetric strain is change in volume per unit volume, right? Change in volume per unit volume. Put here, you will get that is equal to sigma by delta V by V, or K can be written as sigma V by delta V. This is the bulk modulus. So we have written the bulk modulus as sigma V by delta V, right? Put here in this equation, equation number 1, put in 1, what we are getting is E will be equal to 3 times, put the value of K, sigma V by delta V, that is sigma V by delta V, 1 minus 2 mu. From here, find out delta V, and delta V will be equal to 3 sigma V by E, 1 minus 2 mu, right? This is the change in volume. And if the material is incompressible, then delta V is 0. It means that 3 sigma V by E 1 minus 2 mu is equal to 0, right? But this cannot be equal to 0. This term, the 3 sigma V by E cannot be equal to 0, right? So 3 sigma V by E, these are the definite values, and these cannot be equal to 0. It means that 1 minus 2 mu is 0. And it also means that if 1 minus 2 mu is 0, it means that mu is equal to 1 by 2 or 0.5, right? So this is how we obtain the relation, the value of Poisson's ratio for a perfectly incompressible material, right? So for perfectly incompressible material, the Poisson's ratio is given by 0.5, right? I hope that you understand this concept, that from where we have got the value of Poisson's ratio as 0.5, right? So we can proceed further. Let us take one more example of elastic constant. Let us take this question. This is a good question. So let us solve this question. In this question, it is asking that this was the question asked in GATE 2016. The question was asked in GATE 2016. And what is that question? Let us discuss. Let us discuss. A square plate of dimensions L by L. There is a square plate. L is the one side and another side is also L, right? L by L dimensions is there. And a uniform pressure of 250 megapascal is applied. So this pressure is applied, this pressure on all sides is applied, right? This pressure is applied, and the value of this pressure is given 250 megapascal. As shown in figure, the deformed shape is a square. When this is deformed, the shape is again a square. Again a square shape is there with length this. Now the side is this, right? L minus 2 delta, right? So it means that dotted line, this dotted line has the side of, this has the side of L minus 2 delta. This is the side, right? L minus 2 delta. Also the values are given. L is given 2 meters. So L is given 2 meters. L 2 meters is given. And delta is given, that is 0.001 meter. These two values are given to us, right? L is given and delta is given to us. Is it okay? Now, E is also given to us. E is also given to us, that is 200 gigapascal. We have to find out the Poisson's ratio. What is the Poisson's ratio in this case, right? What will be the Poisson's ratio for this material, right? So, because we are going to use the volumetric strain here, we know the formula, the same formula we are using, that volumetric strain is given by sigma x plus sigma y plus sigma z upon E 1 minus 2, right? We know this formula, right? Here sigma x and sigma y are equal. Sigma x and sigma y are equal. That is given by the pressure applied. P pressure is applied, and that is 250 megapascal. But there is no sigma z here. Sigma z is 0. So sigma z is 0. Yeah. Right. So sigma z is 0. But we are talking about volumetric strain, volume. So we can assume that this square plate have some small thickness T. So this square plate, basically, this plate have a small thickness T, so that we can apply this volumetric strain concept here, right? Because it is having slight thickness, small thickness T. It is having a small thickness T. Right? T is the thickness of this material. This is the thickness T, small thickness T. And the pressure is applied in two directions, that is X direction and Y direction. This is the pressure applied, P. Equal pressure is applied in both directions, X and Y direction. Equal pressure, right? And there is a small thickness T, right? So what is volumetric strain? What is volumetric strain? That is change in volume per unit volume. Change in volume per unit volume. So what is the volume of this material? Volume of this material is, that is the L into T, thickness. So this is L square T, right? T, we have assumed the thickness of this material, right? T is the thickness of material, right? And suppose this is initial volume. This is initial volume. Finally, when it is deformed, the final volume is Vf. That is the side becomes L minus 2 delta, right? You can see here, this is L minus 2 delta. So this is L minus 2 delta square multiplied by T, right? So this is initial volume and this is final volume. So what is change in volume? What is change in volume? That is equal to, we can write in positive sense, right? Because Vi minus Vf, because initial is larger and final is less. So we can write Vi minus Vf. Actually, it is Vf minus Vi, but in positive sense, we can write Vi minus Vf. Then we will take T as positive, right? Otherwise, we have to take T negative, right? So that is not a problem. So delta V is initial volume minus final volume we have taken here. It will come out positive. So P we will take positive in our numerical, right? So here, so volumetric strain is delta V by V, and which is equal to sigma x plus sigma y, which is P. So it will be 2P by E into 1 minus 2 mu. So what we have to find out is Poisson's ratio. So from here we can find out the Poisson's ratio. Delta V by V is equal to 2P by E 1 minus 2 mu, right? So this is the relation. So put in this equation the values. Delta V is change in volume, initial volume minus final volume. So initial volume is, I am writing here with red. I am writing here. So initial volume is L square T. Initial volume is L square T. Final volume is minus final volume, that is L minus 2 delta. L minus 2 delta whole square into T divided by the actual volume, final volume, that is L square T, and that should be equal to 2P by E 1 minus 2. So again we can write that from here T will cancel out. T will cancel out. So we can write L square minus L minus 2 delta whole square by L square. T is cancelled out. That is 2P by E 1 minus 2. So now put the values and get the answer, right? So you will get mu by putting the values. L we know, that is 2 meters. So we can write L square as 2 square minus L is 2 minus 2 delta. Delta is given to us, that is 0.01001 square by 2 square, that is equal to 2 times P. What is P? P is given to us, that is 250 megapascal divided by E. E is given to us, that is 200 gigapascal, converted into megapascal, multiplied by 10 by 3, 1 minus 2 mu. 1 minus 2 mu. How many unknowns are there? How many unknowns are here? Only one unknown, right? In this equation, how many unknowns are there? Only one unknown, right? So by using the calculator, solve it and you will get the value of Poisson's ratio, right? And the value of Poisson's ratio will come out to be, So value of Poisson's ratio, when you solve it, solve this equation and get the value of Poisson's ratio mu, and that will come out to be 0.1. 0.1. So this is the value of Poisson's ratio, right? Isn't it? Right. So how do we solve it? We have used a square plate at which a pressure is applied. We have made a three-dimension body, right? Assuming that it is having very small thickness T, right? So that we can use the volumetric strain concept. So there is volumetric strain given by this equation, that is volumetric strain is equal to sigma x plus sigma y plus sigma z by E1 minus Q mu. Now volumetric strain is delta V by V, and stress given is sigma x sigma y, and this stress both are equal, and that is equal to the pressure applied. Put here and you will get the volumetric strain as delta V by V is equal to 2p by E1 minus 2 mu. This equation will come out, right? Here put the value of delta V, initial volume minus final volume, by V, initial volume, equal to 2. Pressure is given to us, E is given to us, and we can find out the mu, right? So this is how we can find the question of, we can solve the question of elastic questions, right? Let us solve one more question on thermal stresses. Thermal stresses. Let us solve one question on thermal stresses. Basically, let us have a brief idea of thermal stresses, that if a body is there which has a temperature of, suppose it has some initial temperature, and the temperature of the body is increased by, suppose, delta T. The temperature of the body is increased by delta T, right? Due to this, there is expansion in the body, expansion in length of the body, right? We are giving a brief discussion of the thermal stresses. What are thermal stresses, right? So you should remember this. We are discussing the thermal stresses. There is a body, a bar, at which the temperature of this bar is increased delta T, right? Now, suppose it has a length of L, and alpha is the coefficient of thermal expansion. Alpha is the coefficient of thermal expansion, coefficient of thermal expansion of this body. Then there is increase in length of this body, and this increase in length is given by L alpha delta T. So this is the change in length of the body due to temperature rise, that is L alpha delta T. This is the rise in, increase in length or elongation of the body, L alpha delta T. Now, if the body is free to expand, if body is free to expand, there is no stress developed, right? कोई स्ट्रेस डेवलप नहीं होगा अगर ये बॉडी फ्रीली एक्सपेंड हो रही है, राइट? स्ट्रेस कब डेवलप होता है आपके माइंड में? स्ट्रेस कब डेवलप होता है? जब आपको रोका जाए कुछ काम करने से। मॉलिक्यूल्स दूर जाना चाह रहे हैं, एक्सपेंड होना चाह रहे हैं, और हम उनको एक्सपेंड होने दे रहे हैं क्योंकि टेम्परेचर राइज हुआ है, राइट? तो एक्सपेंड होने दे रहे हैं तो कोई स्ट्रेस डेवलप ही नहीं होगा। स्ट्रेस तब डेवलप होगा जब हम उसको रेस्ट्रिक्ट कर दें, रेस्ट्रिक्शन दे दें, एक्सपेंड ना होने दें, राइट? सो स्ट्रेसेस विल डेवलप. Stresses means which stresses? Thermal stresses, right? Thermal stress will develop when there is restriction, to expand. यानी कि हम उसे एक्सपेंड होने नहीं दे रहे हैं, तब थर्मल स्ट्रेस डेवलप होंगे, अदरवाइज थर्मल स्ट्रेस डेवलप नहीं होंगे. तो कैसे किया हमने? थर्मल स्ट्रेस कब डेवलप होंगे? In this case, free expansion, this is free expansion. First case is free expansion, this is the first case. And there is no stress developed, right? So sigma is 0, no stress developed, right? But when the restriction is when their expansion is restricted by suppose rigid wall. Suppose this is restricted by rigid wall. Rigid wall is there, right? And there is free expansion, but we are not allowing the free expansion. It means some force is there which is compressing this material, right? So compressive stress will be developed. If the temperature is raised by delta T, there is delta T temperature rise, there is compressive stress developed, sigma, right? So in first case, if we talk about first case again, what was the strain developed? Strain developed in first case, that is the change in length upon original length. So that will be, that was L alpha delta T upon L. So this is alpha delta T. The strain was alpha delta T. So strain was alpha delta T. You have to remember this also, right? Strain was alpha delta T, right? Now, if strain was alpha delta T in first case, in second case there is no strain. In second case, case 2, expansion is restricted. Expansion is restricted. Expansion is restricted. In this case, when the expansion is restricted, it means that the delta L change in length is 0. Also the strain is 0, but there is some stress developed, right? There is some stress developed. Is it okay? And what is the stress developed? You can think that there is some, this deformation, there is some load which is causing this free expansion to be suppressed, right? This expansion is suppressed, right? And we know that L alpha T, which is suppressed, that should be equal to, if this is load, the suppression by load will be equal to PL upon AE, right? From the simple stresses cases we know PL upon AE, and that will equal to load upon area is stress. So sigma L upon E. So this will come out to be L to L cancel. So this will come out to be stress will be equal to E alpha delta T. So this is the stress developed in the material, right? When there is restriction is there, right? Expansion is restricted, right? So this stress is developed. This is compressive stress in this case because the temperature is raised. So E alpha delta is the stress. E alpha delta T is the stress. Alpha delta T is the strain in first case, and expansion was there in first case was alpha L alpha delta T, right? So these three formulas are important for thermal stresses. Now we can solve this question. Now we can go for this question, right? How to solve this question? So in this question, it is given that a solid cube of side 1 meter. A solid cube is there. A cube is there. This is the cube. This is the cube, right? This is a solid cube, and room temperature is 32 degrees centigrade. Means initial temperature is given. Initial temperature, that is 32 degrees centigrade. Final temperature is given 42 degrees centigrade. Final temperature is given 42 degrees centigrade. So what is the rise in temperature? Rise in temperature, that is 10 degrees centigrade, right? So this is 10 degrees centigrade rise in temperature. So rise in temperature is 10 degrees centigrade. Bulk modulus is given 200 gigapascal. Bulk modulus is given K. K is given to us, that is 200 gigapascal. 200 gigapascal is the bulk modulus. This is also given. And coefficient of thermal expansion. Coefficient of thermal expansion of this material is also given. Alpha. Alpha is given. That is 1 into 10 to the power minus 5. 10 to the power minus 5 per degree centigrade. Alpha is given. It is given that the cube is constrained. Constrained. This is very important line. Constrained means it is not expanded. It is not allowed to expand. It means that there is some restriction. There is restriction on this cube to expand. It cannot be expanded, right? There is some rigid walls are there which is causing this cube to be restricted for expansion, right? So expansion is restricted and the temperature is raised. So temperature is raised by 10 degrees centigrade, but there is constraint that it cannot be expanded. So there is restriction in the expansion. Restriction in expansion. This is given to us. Restriction in expansion, right? And there is 10 degrees centigrade. So stress will be developed because we already discussed that when there is no expansion is not allowed, then the stresses are developed. So stress is developed now, right? So we have to find out what stress is developed in this case, right? What is the stress developed in this case? This we have to find out, right? So how to find out this? No, it is this is a cube. This is a cube, and because it is restricted from all sides, so there will be compressive stress because it will try to expand, and some force will be there which is compressing this, right? This expansion, we can assume that, right? It means that there is stress developed in all directions. Stress developed in all directions. Sigma stress is developed in all directions, right? In x direction, in y direction, and in z direction. The compressive stress will be developed, right? Because expansion is restricted, right? Some stress, some force is there which is compressing this material, right? So stress is developed, and this stress developed will be compressive in nature. Compressive in nature, right? So this is known that compressive stress will be developed, right? Now, what is bulk modulus? What is bulk modulus? That is stress upon volumetric strain. Here this volumetric strain is not there, but volumetric strain is restricted here, right? So this epsilon V is strain restricted basically. Strain restricted, right? Here the strain is restricted, right? So if strain is restricted, a volumetric strain, and what is the strain in this material, right? What is the strain is restricted? We know that in one direction, volumetric strain is basically the strain in all direction, epsilon x plus epsilon y plus epsilon z, right? The strain in all direction. And here, because it is uniform, so epsilon x will be equal to epsilon y will be equal to epsilon z, and that will be given by, strain. We have already discussed that this is given by alpha delta t. Alpha delta t, right? We have discussed in the previous slide, right? So here the volumetric strain will be equal to epsilon x plus epsilon y plus epsilon z. So this will become 3 alpha delta t. So this is the volumetric strain, 3 alpha delta t, right? Now volumetric strain is 3 alpha delta t. So we can write we have to find out the stress. So from this equation, we can find out the stress now, mean stress. This sigma is the mean stress, right? So this is equal to K epsilon V. K epsilon V, right? So K is given to us, epsilon V we have already found out. So this is K times 3 alpha delta T, right? So stress is basically 3K alpha delta T. So this is the stress. Put the value and get the answer, right? So 3K, what is the value of K? 200. What is alpha? 10 to the power minus 5. What is temperature rise? That is 10 degrees centigrade. So 10 degrees centigrade or 10 Kelvin is immaterial when there is temperature rise, right? When there is change in temperature, so degree centigrade or Kelvin is same, right? So from here, we can find out the value of that sigma. Now we can find out the value of sigma as, the value of sigma will be equal to, solve it and you will get the value of sigma. So the value of sigma will come out to be 60 megapascal. 60 megapascal. Use your calculator and you will get this value. 60 megapascal. So this is the answer of this question, right? So this question was asked in GATE 2019. This is basically the combined effect of elastic constants and temperature stresses, right? Thermal stresses are there, as well as we used the concept of elastic constant, bulk modulus here we have used, right? The concept of bulk modulus, right? So in this case, what we have done is we have used the volumetric strain concept. That volumetric strain is the strain in x direction, strain in y direction, strain in z direction, and because restriction is there in all directions, so strain will be same in all directions, right? So strain restricted is same in all directions. So epsilon x, epsilon y, epsilon z will be equal to alpha delta t. So the volumetric strain will be 3 times alpha delta t. 3 times alpha delta t will be the volumetric strain. Now, we know the formula of bulk modulus, that bulk modulus is given by K is equal to sigma by epsilon V. So from here, we can find out sigma, which is sigma is here the mean stress or direct stress, right? Sigma here is the direct stress or mean stress, which we have to find out, right? Direct stress or mean stress, right? So sigma equal to K times epsilon V, and K times epsilon V we have used here. So put the value of epsilon V from here, 3 alpha delta T. So 3K alpha delta T is the stress in this material, right? So 3K alpha delta T is the stress, right? Put the value, numerical value, 3K is given 200, alpha is given, temperature rise is given. So you can find out the stress, direct stress in megapascal, right? So this is how we can solve the questions of thermal stresses and elastic constants, right? So uh, we will meet again. We can close the class here now. We will meet again on Saturday at 8 o'clock next week. So we will take some gate questions again. We will take one more topic of the gate, and then we will solve some questions of the gate. First, we will summarize that topic, the formula which we have to use in our numericals, and then we will solve some of the good questions of the gate exam or any other questions out of the gate exam or engineering services exam. We will solve these questions also, right? So that is all for today. uh, I'm going to close the meeting now. So best of luck. Good night for all.